Most people never realize just how advanced modern water wells have become. When we imagine a well, we think of a simple stone circle in the ground, a rope, a bucket, and clean water just a few meters below. But today, especially in regions struggling with long-term drought, that picture is completely outdated. In many parts of the world, groundwater has dropped hundreds of feet below where it used to be. Aquifers that were once full are now shrinking as rainfall decreases, temperatures rise, and water demand increases. As a result, modern water wells must reach extreme depths, sometimes 800, 900, or even 1,000 feet straight down, deeper than the height of many skyscrapers. These modern wells are nothing like traditional open wells. They are narrow, precision-drilled boreholes, designed to cut straight through layers of soil, rock, sand, and clay until they finally reach the hidden aquifer below. These aquifers are the lifelines of many communities, especially in places where surface water, like lakes and rivers, has dried up or become unreliable. For thousands of families, these deep wells provide the only dependable source of clean water. Inside each one of these deep boreholes is a powerful submersible pump. Its job is incredibly demanding. It must push water up from nearly a quarter-mile underground and deliver it to the surface with enough pressure to supply entire households, farms, or even small towns. But at these extreme depths, pumps operate under conditions most machines were never designed for. Several challenges come into play. Falling water tables mean the pump has to work harder and for longer periods. A sand intrusion from shifting underground layers can scratch, jam, or wear down moving parts. Heat buildup is a major issue, because the deeper the pump goes, the harder it is for heat to escape. A mechanical fatigue sets in faster, as motors, wires, and pipes must support tremendous pressure. Eventually, even the strongest pump will fail. But this is where the real challenge begins. When a pump breaks at a depth of 800 or 1,000 feet, technicians cannot simply pull the equipment out by hand. These systems weigh hundreds of pounds, span hundreds of feet, and are often tightly wedged inside the narrow shaft. That's why special teams, trained in confined space vertical descent, must be called in. These specialists perform one of the most intense and technical jobs in the water industry, descending directly into the well. Wearing heavy protective gear, they attach themselves to harnesses connected to controlled winches. They slowly lower themselves into the shaft, sometimes inch by inch. Constant communication with the surface team is essential. Inside the well, space is extremely tight, only slightly wider than a human body. There is no room for error. A descent of several hundred feet might take only a few minutes, but it requires incredible concentration. The deeper they go, the darker and more silent the environment becomes. Temperature and humidity change, and the air becomes heavy. Once they reach the pump assembly, they must inspect every component, identify blockages or damage, and either reposition or repair the equipment, all while suspended inside the narrow shaft. It's a job that demands strength, precision, and absolute trust in the team above. This entire process shows how far modern groundwater extraction has evolved. What used to be simple, just digging a shallow well, has transformed into a highly technical field involving geology, advanced engineering, and specialized labor. But it also highlights something bigger. Our environment is changing, and engineers must adapt with it. As aquifers continue to decline due to overuse, climate change, and growing populations, wells are pushed deeper, equipment becomes more complex, and repairs become more dangerous. Modern deep wells are both a technological achievement and a warning sign. They reveal how much we depend on groundwater, and how urgently we need to protect it.